So today we will look at congruences again, and first thing that we'll discuss is cancellation. Okay, because you know that if you have an ordinary equation like ax equal to ay in integers, you can cancel a as long as a is non-zero. So if a is non-zero, you can cancel a from ax equal to ay and you get x equal to y. Now when we go to congruences, it is similar but not exactly the same. So we have to be somewhat more careful when we do cancellation. So this theorem says that suppose AB is congruent to AC modulo n, then we can say that B is congruent to C modulo not original n, but we have to factor out the GCD. Suppose D is the GCD of A and N. A is this coefficient, so to speak, and N is this modulus. Okay, so we have to factor out this. Okay, so it's not that AB congruent to AC modulo N will give you B congruent to C modulo N. This modulo N factored out by D, where D is the GCD, and it is not difficult to prove. So let me just prove it first. So okay, so yeah, this should have been D again. Okay, so since D is the GCD, okay, so if GCD of A and N is D, so there will be co-prime integers R and S such that A is dr and N is ds. Okay, remember that GCD, this GCD is D. So once I take out the GCD, whatever remains, suppose A by D and N by D. So A by D is R and N by D is S. And we showed before that once we factor out the GCD, two integers are co-prime. I mean, that actually is obvious from also unique factorization of integers into product of primes. That way also one can see it is. But even more basic is the property that GCD is a combination of A and N. Like suppose AX plus NY equal to D. Then I can divide both sides by D. So A by D times X plus N by D times Y is D by D, which is 1, which shows that A by D and N by D are co-prime. So A by D is R, N by D is S, and R and S are co-prime. Unfortunately, this is actually D. This is not 1. Okay. Now let's see what we can do with this. Now we have this given congruence, okay, which you can write like this. That it is by AB minus AC is some multiple of N. And this I can take A as common factor. Now what we are going to do, we are going to replace A by dr and N by ds. Okay, so what we are getting is D times R times B minus C is K times D times S. Okay, from which clearly we can factor, because this is now in integers, it is an equality. This is no longer a congruence but an equality. And we can factor out this D because it's not 0. So we can get R times B minus C is Ks. Okay. Now let's see what we can get out of this. That we see this as S dividing this product where S and R are co-prime. So S divides R times B minus C, but S is co-prime to R. In this situation, S must divide B minus C. Okay, so S must divide B minus C, which in other words, basically B is C mod S. And that is what we wanted, because S is nothing but N by D. Okay, another typo. This is N by D. Because remember, what is S? S is N by D. This is N by D. So we get the desired result. Okay, and of course these facts we proved already, that when an integer divides a product, and if it is co-prime to one of the factors, it will divide the other factor fully. Again, these are all consequences of GCD being a combination of the two integers. Okay, we did all that, so you can just use this. There are two typos. Here it should have been D, and here it should have been N. Anyway, I'll correct it when I upload the notes. And the corollary, the best thing is when A and N are co-prime. When A and N are co-prime, then N by D is basically N by 1, which is N. Okay, so when A and N are co-prime, we can actually cancel just like in integers, that AB congruent to AC mod N, in fact, will imply B is congruent to C mod N when GCD is 1. Okay, because we'll be factoring out just 1, which does not change anything. Okay, this is quite useful. Okay, this is cancellation. Okay, this is linear congruence. Okay, so this A is missing here. Linear congruence. So what do I mean by linear congruence? Okay, so the linear congruence is an equation of this form: AX congruent to B. Okay, a linear equation in one variable would have been AX equal to B. You will need to solve. Okay, so okay, so you want to solve this equation AX congruent to B mod N. Okay, this as a solution, we'll say that the GCD of A and B must divide N. A GCD of A and N must divide B. That's the, otherwise this will not have solution. So it's an if and only if condition. But if the GCD of A and N divides B, it will have a solution. And if it does not divide, it will have not solution. And then how many solutions are there? Because when you solve an equation, there are two questions are important: existence of solution and uniqueness of solution, or how many solutions are there. Okay. Of course, if it had been an equation in, say, rational numbers, X equal to B, we know that it is a unique solution. But modulo N, this need not be unique solution. It will have D distinct solution. Okay. So it will have D mutually incongruent solutions, because when we are solving congruence equation mod N, we will need solutions modulo N. Okay, if two, suppose we want to solve modulo 6. Okay, then for that, for us 1 and 7 will be same. So if 1 is a solution, basically that will automatically mean 7 is a solution. So we'll be interested whether if we have one solution 1, whether 4 is a solution, that will be interesting. But whether 7 or 13 is a solution, it will not be interesting, because they are same mod 6. Okay. So we want solutions which are incongruent modulo N. Okay. Okay, let's see why this is a necessary and sufficient condition. Okay, suppose this is a solution. Suppose this is a solution. We'll have to show that the GCD divides B. Okay, so suppose X naught is a solution of AX congruent to B mod N. Then what we can say? We can write AX naught minus B is a multiple of N. Okay, the meaning is AX naught minus B is a multiple of N. Okay, but that gives us AX naught plus NQ naught is B. And now you look at the GCD. GCD of A and N, it divides this as well as this. Okay, D divides A and D divides N, so certainly D divides B. So it is almost immediate, the necessary part, that if this linear congruence has a solution, then the GCD of A and N must divide B. And the converse will also be true. Why? The converse should be true because if the GCD of A and N is D, then we know that there exist integers x naught and y naught such that ax naught plus ny naught equal to D. Okay. Now we have B as a multiple of D. Suppose B is a multiple of D, we want to show that this will have solution. Okay. So what we will do? We know that B is k times D. So we'll multiply this equation both sides by k. So I'll get a times kx naught plus n times ky naught is kd. but KD is B. So, and this is a multiple of n. So if I take mod n, A times Kx naught is congruent to B mod n. So I am getting the solution Kx naught. What is this K and what is this X naught? Is X naught was involved in writing the GCD as a combination of A and N. What is the K? B was K times D, because D divides B. Because remember, conversely, we are showing that if D divides B, so that means D times some K is B, and that case we can use. Okay, so we get a solution. So this is a necessary and sufficient condition. The GCD of A and N should divide B. Okay, so this is one part. That is a solution if and only if this. But what about all the solutions? What are the solutions? Okay, what are the other solutions, or what are all the solutions? Okay, so suppose we have one solution X naught, then we can clearly check that X naught plus n by d times t, where t runs from 0, 1 up to t minus 1, is also a solution. Why? Because I just substitute. I substitute A times this number, X naught plus n by d times t. Okay. What do I find? I find Ax naught plus, since d divides A, so I can write this n by d times A as n times A by d. Knowing that this is some integer. See, we don't want some fraction here. Because if it's an integer, that means it is the whole thing is a multiple of n. So mod n, this is 0. Okay, it's a multiple of n. So this is basically reduces to mod Ax naught mod n. Okay. Okay, I mean, no, normal. I mean, this parenthesis ideally should be put here. Anyway, I'll correct this. So this parenthesis notation wise, this should be after the n. Okay, so this shows Ax naught. But what is my X naught? My X naught is a solution to Ax naught congruent to B mod n. So if X naught is a solution, so is this. What about T? What T works here? Any T works actually. Okay, but we are adhering to only these ones, because we'll show that anything, any other T, I mean any solution will be congruent to one of these. Okay, so in fact for any T, this is a solution, but we want distinct solution modulo n. So taking T from 0 to d minus 1 is enough. Okay, for example, if I take T to be d again, suppose 0, 1 up to d minus 1. Suppose I take T to be d, then what happens here? I get X naught plus n by d times d. So I get X naught plus n. But X naught plus n is congruent to X naught modulo n. So we are not interested in obtaining X naught plus n as a solution once we already have X naught as a solution, because X naught plus n and X naught, they are congruent mod n. Okay, that's why we take up to 0 up to d, but these are sufficient. These many are sufficient. So to show that these many are sufficient, we need to show that suppose I have any other solution. Okay. And okay, so there are two things to be shown. First thing is that they are all distinct. It should not happen that X naught plus n by d times t is also congruent modulo n to X naught plus n by d times some t dash. That should not happen. In other words, we don't want these to happen, because if they are same mod n, we are not getting distinct solutions. Okay, so suppose we have this equal to this modulo n. Okay, and what can I conclude? I can cancel this X naught. Okay. Okay, and if I cancel this n, so first I cancel this X naught, so I get n by d times t is n by d times t dash modulo n. But remember, what is the GCD of n by d and n? It is d. Okay. Oh, sorry. What is the GCD of n by d and n? It is n by d. So if I divide n by d, I get d. So this implies t is congruent to t dash mod d. Okay. It is our original equation. AB equal to AC mod n implies B congruent to C mod n by GCD of A and n. So here GCD of n and n by d is n by d. And so if I factor out n by d, I get n by d. So that I'm getting d. So that means I'm getting these solutions, if they are to be same mod n, the only possibility is that t should be t dash mod d. But however, in our choices, we are taking t from 0 to d minus 1. So if I put t and t dash from 0 to d minus 1, and suppose they are congruent, only possibilities they have to be same. Okay, t has to be same as t dash. Okay, because both of them are lying between 0 and d minus 1. So if t minus t dash is a multiple of d, suppose let's say t dash is let's say t is bigger than t dash, and t minus d dash is a multiple of d, and we are saying that that multiple is basically 0 times d. Otherwise, t will be t dash plus d times 1, suppose. That means this t will go out of the range d minus 1. It will be some non-zero multiple of d, I mean some positive multiple of d plus something non-zero. So it will go out of that. So only way to stop this is not just mod d, in fact they are equal. Okay. Is there any question? Okay, so what we are saying that these are distinct solutions mod n, or mutually incongruent solutions. Okay, so far what we have done, we have said that this congruence has at least the distinct solution mod n. Okay, it has the distinct solution. But now we have to show that there are no more solutions. Okay, we are still one step. We have to do one more step. Okay, first we showed that solution exists if the GCD divides B. Secondly, we showed that if X0 is a solution, so are these ones, and these are all distinct mod n. Finally, I have to show that if I pick any other solution Y0, then Y0 has to be one of these. Y0 has to be X0 plus n by d times t for some t in this range, modulo n. Okay, so how do I do that? We need to show that if I take any solution Z0, it has to be one of these. Okay, how do I do this? Because I know that both X0 and Z0, their solution of AX0 congruent to B. So that means AX0 is congruent to AZ0. That means X0 congruent to Z0 modulo n by d. Because remember that AB equal to AC mod n implies B congruent to C modulo n by d. So I'm just using that. So I get this. And what does it mean? That means Z0 is X0 plus a multiple of n by d. Okay. This means Z0 is X0 plus a multiple of n by d. And now what is my aim? My aim is to show that this K can be chosen from this. And remember, we are interested modulo n. So we want Z0 mod n to be one of these. So this K, we want to see that it's enough to take K from 0 to d minus 1. Okay, so how do I do that? I use division algorithm. Okay, so I divide K by d. So if I divide K by d, I'll have a remainder which will lie between 0 and d minus 1. Okay, because by division algorithm, any K, I divide by d. So I get like this. Then what happens? Then what is my Z0? Z0 is X0 plus n by d, K I replace by this. So that this thing fact cancels out d and d. So I get X0 plus some multiple of n plus n by d times t. Now this nq I can ignore, modulo n I can ignore this because this is 0 mod n. And remember that this t being a remainder upon division by d, it is between 0 and d minus 1. So it is n by d times t, where t is in the desired range. So any other solution, any solution we take can be captured by this mod n. Okay, so that's all we need. And in particular, if we have this mod n is missing, that linear congruence Ax congruent to B mod n has a unique solution modulo n if GCD of A and n is 1. Because see, how many solutions we are getting? We are easily getting D solutions. Okay, we are getting D solutions. But if D is 1, basically we are getting one solution. Okay, we are getting only, because then it becomes x naught plus nt. Okay, anyway, that becomes meaningless because t will be now 0. So we'll get one solution when d is 1. So the best situation is when A is congruent to n, where is we are trying to solve Ax congruent to B mod n. Okay. So this is the corollary. Okay. So we'll demonstrate this by an example. But if you have any question, you can ask me now. Okay, fine. I suppose you don't have any question. Okay, so let's look at an example. Okay, so let's solve this congruence. 18x congruent to 9 mod 33. Okay, so first step, you just check that GCD of 18 and 33. Okay, which is clearly 3. It divides 9. Okay, again I made a mistake, I suppose. Okay, anyway, I made an error. I'll come to that. Okay, so the linear congruence has a solution. Okay, GCD divides 9. So by Euclid's algorithm, how do I solve? I mean, first I have to write the GCD as a combination of this 18 and 33. So we perform Euclid's algorithm to this, so that I can solve 18x plus 33y equal to 3, which I should multiply and get the 9 as a solution. Okay, so as before, probably I did not multiply by 3. I will find out soon. Okay. So anyway, let's apply Euclid's algorithm first. So I get this. At 33 I divide by 18, I get 15. 18 I divide by 15, I get 3. And 3 divides 15, so 3 is the GCD. So I will get 3 as a combination of 33 and 18. How? Because 3 is 18 minus 15, and this 15 I write from this one, 33 minus 18. So basically this. Okay, so yeah, so some typos are there. This should be 3. 3 is 33 times, this should be minus 1. Okay, so there are typos. 18 times 2, clearly I mean it is 36 minus 33. Okay, 3 is 18 times 2 minus 33 times 1. So that is the one I need, because I need the GCD as a combination. Then to solve this, I'll multiply this by 3 once more. Then I'll get 9 to be 33 times minus 3 plus 18 times 6. So I'll get 6 as a solution. Okay, 6 should be a solution. Okay. Okay, so one can verify that 6 is a solution. Okay. Yeah. So yeah. So but yeah, unfortunately there are some typos here, so which makes it. Okay. I mean, okay. So I can, one way to correct this will be like, let's make it 18x mod 3. Okay. Then I do not have to do the multiplication. Okay. And remember, this is not 18. It is actually 3, and this is 18 times 2 plus 33 times minus 1. And again, this part we don't need. I just need this 2. Okay. But I made a mistake here that I didn't wrote 9, but I forgot to multiply this equation by 3 in the subsequent page. Okay. Okay, so x naught congruent to 2 mod 33 is a solution. Well, if my original equation was 3, then it is a solution. Otherwise, I have to multiply by 3. Okay, so bear that in mind. And but other solutions will be, this is the GCD. I mean, this is n by d. Okay, times t. T should be 0, 1, and 2, because GCD is 3. So t will run from 0, 1 and 2, and it will be 2 plus 11t, where t is of this form. Okay, so basically t equal to 0, 1 and 2 I should put, but this is actually giving me solution to 3. Okay, I suppose. So 2 times 18 will give me 3. So if my actually equation was 9 as I wrote, then I have to multiply it by 3 times. So my solution should be 6 here. Okay, so this solution for 18x congruent to 3 mod 33, the solution is 2 as I stated, but for 18x congruent to 9 mod 33, I just have to multiply by 6. So one can probably verify that 6 into 18, okay, then you subtract 9, you get 99, which is multiple of 3. Okay, so remember that these solutions should be like 6, then 6 plus 11, which is 17, and 6 plus 22, which is 28. So the solutions are actually slightly different than this. And I'll correct it when I upload the lectures. Okay, any question? Okay, my problem is that I forget to multiply. Even earlier also there was an error earlier that in one of the earlier classes that I did not multiply, and some of you pointed out that I have to multiply at the end by the suitable multiple. So same thing here, I have to multiply by 3, so that this 3 times 3 becomes 9, and this becomes 6. 18 times 6 plus 33 times minus 3, which should be 9. Okay, because it's clear that 18 times 6 plus 33 times minus 3 is like 108 minus 99, which is 9. Okay, that's what we would have wanted. So the solution is 6. And with 6 as solution, it will be others are 6 plus 11 and 6 plus 22. Okay. Okay, so now let's come to a very important theorem, which is known as the Chinese remainder theorem. Okay. So what the Chinese remainder theorem tells us, suppose we want an integer which leaves certain remainders when we divide by some other integers. Okay. Suppose I want an integer which has remainder 7 when I divide by 18 and has remainder 5 when I divide by 35. Okay, like that. Okay, remember what is special here? 18 and 35. It is based when 18 and 35 are co-prime. Okay, 18 and 35 are co-prime. So if we want desirable remainders when we divide by co-prime integers, that can be 2 or finitely many, in fact, that problem has a solution. Okay, so it is like so what we are effectively, so that's like a simultaneous congruence equation that we want to solve. Why? Okay, so first of all, let these be positive integers which are pairwise co-prime. What do I mean? Their GCD, okay, this comma is missing. The GCD should be 1. The GCD of Ni and Nj should be 1. Okay, like 18 and 35. Then what I can do, I can consider these simultaneous congruences. X congruent to A1 mod N1, X congruent to A2 mod N2, and X congruent to AR mod NR. Then this is a simultaneous solution. And this solution is unique modulo the product of these integers. Okay. So in other words, it's like, suppose this is like 35 and 18. So basically it's like I want an integer which leaves remainder A1 when I divide by 35 and leaves remainder A2 when I divide by 18. So that's why it's like we are fixing the remainder when we divide by some co-prime integers. And then we want to look at common solutions. Another way to view it is, okay, we discussed how to solve one linear congruence. So suppose we have more than one linear congruence. How do we solve? Okay. How do we solve? more than one linear congruence. Okay, to start with, a linear congruence might be AX congruent to B mod N1, but then we can get rid of this A. There's a way to do that. We can reduce it to this form. Anyway, I'll come to that. But suppose we are given in this form. Okay, so how do I solve? This solution is not difficult and it is explicit. The good thing about the proof is it is an effective proof. It tells us how to find the solution, because there are certain proofs which doesn't help in finding the solution. Okay, like unlike Euclid's algorithm, because by well-ordered principle we can say that GCD of two integers a and b is a linear combination of, or it is of the form ax naught plus by naught. And how to find that x naught and y naught? This well-ordered principle does not help too much. But if I apply Euclid's algorithm, it's good because it not only shows existence, but how to find this x naught and y naught. Okay. Similarly, this proof, Chinese remainder theorem, actually tells you how to find the solution. So it's a effective proof. So how do I do? First, okay. So take capital N to be the product of all these N1 up to N. Okay. Let's call this capital N. Okay. And then we fix Ni, this big Ni, that is capital N divided by Ni. So what is that? That means you take all the others except Ni. Okay. You take the product of the remaining modulus, but forget about Ni. So that way I can find N1, N2 up to Nr. So what is N1? Capital N subscript 1. Capital N subscript 1 is like N2, N3 up to Nr. What is capital N subscript R? This N1, N2 up to Nr minus 1. Okay. And for example, what is capital N subscript 3? You take small n1, small n2, then you take small n4 up to small n. You just omit n3 in the product. So that way you pick these integers. Now, what is to be observed is that this Ni is divisible by all the other integers except the ith one, because ith one is missing here. So this Ni is divisible by all nj when j is not I. Okay, so all these others will divide this, but it will be co-prime to the ith one. Why? Because Ni is missing here, and I know that no other factor, so no other modulus can compensate because they are mutually co-prime. So this Ni has no common factor with all the others. So that's why GCD of Ni and this one will be 1. That is important. Okay, so that's what we do. Okay, the GCD is 1. But if this GCD is 1, then what's the advantage? Then there is a solution xi such that nixi is 1 mod ni. Because you know that the linear congruence ax mod b modulo n, okay, x equivalent to b mod n, it has a solution always if a and n they are co-prime. So this will have a solution because GCD of ni is capital Ni and small ni, that GCD is 1, and 1 always divides whatever is there on the right hand side. Okay, in particular here it is 1. So 1 divides 1. Okay, GCD of capital Ni and small ni, they divide 1. So this is a solution. So these solutions are there. So now what we claim is that our solution, our simultaneous solution is A1 N1 X1 plus A2 N2 X2 plus AR NR XR. Okay, you take these N1 X1 N2 X2 and multiply with A1s. What is the A1? That's the original remainder that we need. Okay, we want A1. Okay, this is the A1. A1 N1 X1. Okay, like this. Now what do I need to check? I need to check that modulo N1, modulo N1, it is A1. Okay, modulo n1, it should be this. Modulo n2, it should be a2. Modulo nr, small nr at this, it should be this. Okay, that's what I have to check. Okay, let's check. Let's take this and let's consider modulo. Okay, it should be ni. Okay. So what happens? Okay, let me say n1 maybe. So what happens at n1? Modulo small n1. Remember that is all these n2 etc. divisible by n1, small n1. So these things, modulo n1 they disappear. Modulo n1 they disappear because n2 has small n1 as a factor and this big nr has n1 as a factor. So it's all a multiple of n1. So it is 0 mod n1. So this goes away. Only term that survives is this. But the way we picked x1, n1 x1 is 1 modulo n1. So remember, what is x1? It is n1 x1 is congruent to 1 mod n1. So I get 1. This is actually 1 mod n1. So it is a1 times 1 modulo n1. So x0 is a1 mod n1. Similarly, I can do the argument with 2. So either I should say this is probably I can make the argument the same argument for each I. So I should say here ni. Okay. For example, if I have n subscript r, then clearly all these other terms. Okay. By the way, this xr is also missing here. Ar, nr, xr. Okay. So that's how we can verify. Now, what about this is the existence part. Now, the uniqueness part. Okay. So, what is the uniqueness? Let's say y is any other solution. Okay. We want to say that y is congruent to x0 modulo capital N. This should be capital N. Okay. So, we want to show that y and x0 should be congruent. How do we do that? Okay. So, you look at y. Y is congruent to AI, okay, because it's a solution. Y congruent to AI mod Ni, but X0 is also a solution. X0 is congruent to AI mod Ni. That means Y minus X0 is divisible by Ni. So Ni divides Y minus X0. But that is true for each I. That means Y minus X0 is a multiple of all of them because they are co-prime. Okay. So that's what we need. That y, any other solution is congruent to x0 modulo the product. Okay. So remember what we are using here. If this divides this and something else co-prime to this also divides, then their product will also divide. Okay. If A divides x and B divides x, then AB also divides x, provided A and B are co-prime. Okay, so that perhaps I proved, but anyway, that will not be hard to prove. That if two co-prime integers divide the same number, then their product will also divide the same number. Okay. So that's how Chinese remainder theorem is proved. So let me illustrate this by an example. Okay. So let's take an example. Find an integer that leaves remainder 3 when divided by 8, leaves remainder 5 when divided by 15, and leaves remainder 1 when divided by 7. Important thing is that their GCD 8 and 15 and 15 and 7 and 7 and 8, they are all 1. So solution will exist. Okay, they should be pairwise co-prime. So pairwise co-prime. Okay. Then what we have to take? We have to take capital N, which is the product of all these modulus. So in this case, it is 840. Okay. Then you have to take N1. N1 should be product of the other two. So N1 should be product of 15 and 7. N2 should be product of 8 and 7. And N3 should be product of 15 and 8. Okay. N3 is like N1, N2. N1, capital N1 is like small n1, N2, N3. Okay, like that. So you find this. Now you have to solve this. First, you have to solve 105 x1 congruent to 1 mod n1, small n1, which is 8 in this case. This is like capital N1 and this is the small n1. And good thing to note is that 105 is basically 1 mod 8 because 105 is 8 into 13, I suppose. Yeah, 8 into 13 is 104. So this is basically 1. So basically x1 we can take to be 1 mod 8. Okay. Similarly, you need to solve capital N2 x2 congruent to 1 mod small n2. Okay. But remember, okay, so this 56, you know that it is 60 minus 4. 60 is a multiple of 15. So I can say it is minus 4x2 is congruent to 1 mod 15. Okay. So now how do I solve this? I mean, I can of course apply Euclid's algorithm. That is one way. But without Euclid's algorithm also, sometimes it is possible. I mean, that is also convenient. So it's not that we have to use Euclid's algorithm every time. Of course, I could have used Euclid's algorithm with 56 and 15. That would have also given me. But let's see some other way. So it is like 56 is like minus 4 mod 15. And then, okay, now what do I see? I want to bring it to 1. Okay, and easiest way is multiply by 4, or in fact multiply by minus 4. Here I could have multiplied by minus 4. Multiplying by minus 4 would have given me 16, and 16 is 1 mod 15. Anyway, I multiplied by 4, so I need to do one more step. So I multiplied by 4. So minus 16 is like minus 15 minus 1. So minus 15 is like 0 mod 15. So this minus x2 is minus 11 mod 15. So x2 is 11 mod 15. Okay, which I could have shortened by multiplying by minus 4 here. Okay, and third one is that I have to solve 120 x3 is 1 mod 7. Okay, and good thing is this is again 1 mod 7 because it is 150. 17 times 7 is, okay, you can see that if I divide by 7, it is like remainder 1. So it is x3 is congruent. So x3 can be taken as 1. x2 can be taken as 11. Okay, the solution, okay, just a moment. Okay. Just a moment. Okay, so the solution will be like this is the remainder that we wanted modulo 8. Okay, or modulo n1. So it is like a1 times capital N1, okay, times x1. Okay, like this. Okay, a2 capital N2 x2 and a3 capital N3 x3. So okay, some typos are there, I suppose. Anyway, eventually it is 155. Okay, this 435 is not needed. It's an intermediate number that came, but yeah, maybe if I add these first two terms, I get probably 4. Or adding these two, I got 435. Doesn't matter because this solution is 3515, but I can always reduce mod 840. Okay, so it is 155, and I can verify that 155, if I divide by 8, it leaves remainder 3. And when I divide by 15, it 5. Okay, that is most clear. I mean, 155 is 150 plus 5. Okay, and when I divide by 7, it should leave remainder 1. So 155, if I divide by 7, certainly it leaves remainder 1. And this also can be clearly checked. Okay, so that's how we can use Chinese remainder theorem to solve simultaneous congruences. Okay. Okay, so maybe finally, there is also a terminology maybe I can introduce. which is reduced residue system. What is a reduced residue system? You take only the co-prime residues. Okay, you forget the residues which are not co-prime. Okay, and you take all the ones which are co-prime to n, all the possible residues. Because if you take any integer n, there will be n distinct congruence classes, but some of them will not be co-prime to n. The residues will not be co-prime to n. So you omit those, but take all others. Then it will be all the reduced residue system. For example, let's take 6. I had 6 congruence classes, like 0, 1, represented by 0, 1, 2, 3, 4, 5. But 2, 3, 4, and 0, they are not co-prime to 6. So only co-prime ones are 1 and 5. So I'll take this. Of course, remember that these are just representatives of the equivalent congruence class. So I could have picked, instead of, well, okay, I suppose I made a mistake here. It should be 19 here. Okay, so fine. This example has to be corrected because 11 will be like covering for 5. Okay, but 1 should be covered by 19. Okay, so it should be 11 and 19. That is also another reduced residue system. And this is not a reduced residue system modulo 5. Okay, modulo 5, what is happening? It is covering 3, 4, and 1. Okay, so this 6 is also an unfortunate thing. Okay, this is not 6. This is 1, this is 5, and this is also 5. Okay, so yeah, so modulo 6, this is not a reduced residue system. It's true that they are all co-prime to 6. They are all co-prime to 6. But there is redundancy because 29 and 41, I don't need both. Okay, because any integer should be just congruent to one of them, which is any integer co-prime to 6 should be co-prime to only one of those. Okay. So that is a reduced residue system. Later on, we'll see that there will be phi n of them, where phi is the Euler function. Okay. So why this set failed to be a reduced residue system? Because if I take any integer co-prime to 6, it will be co-prime to one of them, but it will be co-prime to actually, in this case, 2 of them. For example, if I take 5 will be congruent to 29 as well as 41. So that is not desirable. So there is redundancy. You take 13 and 29, which is fine, or 13 and 41 will also be fine. Okay, but if you take only 13, that will not be sufficient because that will not cover 5. For example, 5 will not be congruent to 13 mod 6, and 5 is co-prime to 6. Okay, why reduced residue system is good to have? Later on, we'll see that. See, if A and B are co-prime, so is their product. If A and B are co-prime to n, and so their product is also co-prime to n. Okay, so that way we can define a multiplication on the reduced residue system. It will be closed under that operation, because if I take 2 congruence classes with residues co-prime to n, then their product will also be co-prime to n. So we will have closure property. Okay, we will have closure property for multiplication mod n. In other words, these equivalence classes will have multiplication, and they will have an identity also, because 1 is always co-prime to any integer. So it will have a multiplicative identity. Okay, it will have a multiplicative identity. It will be closed under multiplication, just like integers under multiplication. Okay, ordinary integers under multiplication, they have identity element, like you multiply by 1, you get back the same. And it is closure. You multiply 2 integers, you get an integer. But unfortunately, for integers, you don't have an inverse. That's why you go to rational numbers, because 2 as a integer doesn't have an inverse, multiplicative inverse. So we have to go to rational numbers. But good thing about this set is that it will have an inverse. Okay, why? Because remember that GCD of AN is 1. So we can always, okay, we have given a basic proof that GCD, if A is in the reduced residue system, and GCD of a and n is 1. So I can find integers x and y such that x plus ny is 1. And modulo n, ignore this part. I'm getting, for a, I'm getting some x such that ax is 1 more n. Okay. So I'm getting ax is 1 more n. So in other words, as multiplication of congruence classes, I'm getting a times x is 1. Okay. And why should this x belong to S? Because x is also coprime to n. Okay. X is also coprime to n. Why x is coprime to n? Otherwise, if d divides n and d divides x, d has to divide 1. Okay. So this equation implies, originally we started with a and n which are coprime, but anything here will be coprime to anything there, because x will be coprime to y, x will be coprime to n, y will be coprime to a, y will be coprime to x. Because any common factor will divide 1. Any common factor from these two, any of these, and any with any of these, we will divide this. Okay. So that's why this is something that we can bear in mind, because later on when we have group structure, when we define groups, what are groups, that will be set with some operation, which the operation should have identity and inverse. So whereas integers do not have inverse under multiplication, but if we take the reduced residue system, then we get these equivalence classes, we get the group structure. Okay, so anyway, that will come later. This is just to give an example. This is like, okay, so, but the most important thing to take from this class is the Chinese remainder theorem and linear congruence. Okay, first linear congruence and simultaneous linear congruence. Okay, so yeah, if you have any question, you let me know now. Okay, I'll correct the typos and upload.